So our next speaker is Oriol Serra from Barcelona, who speaks on triangulations and the Brunn-Minkowski inequality. Please, Oriol.
Thank you. Thank you very much for organizing this very nice conference and keep it working in this way. I will talk about joint work with Katsi Borowski and Mate Matozzi and Indra Ruja from Kenya Institute and Paco Santos from University of Cantabria. So everything I will say is joint work, and it's something which appeared in a paper last year, and it deals with this Brunn-Minkowski inequality and trying to make it uh, a good discrete version. So let me start just by reminding this Brunn-Minkowski inequality, which says that if you are in a d-dimensional Euclidean space and you have two compact sets, then the subset has a measure which can be lower bounded by the measure of the summons in the way normalized by the df root. So I think that this is perhaps one of the first results on subsets maybe. And actually this thing of the subset is sometimes called the Minkowski sum.
So, excuse me, Oriol, can you speak a little bit louder, please?
I will. Sorry. So here, this mu here is just the direct measure. So it's the volume of the set. So this is the Minkowski inequality. And so I recall also that the case of equality is characterized, and there is, if none of the two sets have zero volume or zero measure, then the equality holds if and only if A and B are homothetic convex sets. So this is a very nice, additive inequality with the inverse result included. So now the quest is to obtain a discrete analog of these inequalities. And naturally, for these discrete analogs, one would bet for cardinality being the analog of the measure, so the counting measure. But in this case, the results suggest that maybe cardinality is not the right analog for an inequality of this type, for Brunn-Minkowski type inequality. So let me just review a couple more of results which deal with this problem in the discrete case. So you can so we have a finite set. So I should set here finite. You have a finite set in a d-dimensional Euclidean space, so it's easy to see that the coordinates are not rationally dependent, and the subset can be very large. So the interesting case is where you are in a d-dimensional lattice in Z to the D, and there is this classical theorem by Feynman, which says that if you have a set A, which is d-dimensional, so it is not sitting in a hyperplane, then the cardinality of A plus A can be lower bounded by something which depends on the cardinality of A, and the constant is the dimension plus one minus some constant, depending also on the dimension. And this inequality is good. One is witnessed by the fact that it is tight, and the extremal examples are reached, or it can be characterized actually by sets which are parallel arithmetic progressions with the same difference, like in this drawing. So that one may think that so the Brunn-Minkowski for 2 equals A equal B, so the case A plus A, then it gives that the constant is exponential in the dimension, here is linear. So one may think that is because of the structure of the extremal sets that we cannot get a much better or a better inequality. So one quest about these things is how to desymmetrize this kind of uh, inequalities. Instead of talking about A plus A, speaking about two distinct sets. And this is usually more complicated. And, uh, and there is this theorem of Russia which addresses this issue. And again, here there is some condition. So you have two finite sets. Again, oh, here finite is included. You have two finite sets in the d-dimensional lattice z to the d. And I have to require that, that they are not all sitting in a hyperplane. Otherwise, the inequality might not be uh, good. And there is, again, an inequality of this sort where the cardinality of the subset is lower bounded by some function of the cardinalities of the summands. And this function is explicitly given in this theorem, is something. And, there is, again, extremal sets, which I tried to depict in this figure, which are called actually long simplices. So so you just have the minimal number of sets of points to get something which is truly d-dimensional, but the rest is just sitting in arithmetic progression. So these are peculiar sets that maybe uh, just they do not convey what one is trying to capture by these Brunn-Minkowski inequalities. So there is something which resembles much more Brunn-Minkowski inequality, which is this inequality of Gardner and Gronke, which says that if you have, again, two finite sets, A and B, in a d-dimensional lattice, then, well, again, to exclude some degeneracy cases, you require that at least one of the sets is d-dimensional. Then you have something which looks like it's much closer to the Brunn-Minkowski, that the cardinality of the subset raised to the 1 over the dimension is at least one of them. And then the other one, we should set here that this B is the smaller of the two, has corrections, which depend on the dimension. Actually, in the paper, they say that this might be a good inequality because it gives good estimates. I would mention also that one consequence of this inequality is that you get what is called a lattice point enumerator, which means that you have a convex lattice polytope. Then you count the number of points that you have in the lattice in the subset of two convex lattice polytopes, and it gives an inequality for those. So the number of lattice points, so here convex lattice polytopes means that you have this thing, and then you have the convex hull of a point of points, and everything which is sitting inside belongs to the set. So this is we can call it saturated in the lattice, or I think that this denomination of lattice polytopes is quite standard. So you get a lattice point enumerator for the sum of two convex lattice polytopes, and this comes from the inequality here. Okay, so then okay, and this inequality is also tight, and you can characterize the cases of equality for this one. So now starts the story I want to tell you about, and this is a conjecture by Mate and Imre that they made and publicized, particularly Mate, in many occasions, which says that one way of capturing the discrete version of Brunn-Minkowski is perhaps trying to capture some geometric structure of the sets. So you have two sets, again, finite sets. So this is the discrete version. And then you define these uh, triangles of A. That's the number of triangles in a triangulation of the convex hull of the set of points. Yes, so you have a set of points. You just consider the convex hull, and then you triangulate the interior. Now, this is well defined in dimension 2 because every triangulation has the same number of triangles, whatever is triangulation, and this depends only on how many points are in the boundary and how many points are in the interior of the convex hull. And the conjecture is that you have two such sets, then the number of triangles in the subset uh, satisfies this Brunn-Minkowski inequality. That the number of triangles raised to the 1/2 is at least the number of triangles of A raised to the 1/2 plus the number of triangles of B raised to 1/2. That's I think that it is a very nice conjecture because it's kind of an additive relationship which applies to discrete setting, but still keeps part of the geometry inherent to this problem when you are in a d-dimensional lattice. So this, I think, it's my next comment that it captures geometry and by measuring by different thing than cardinality. So another nice feature of this inequality is that it's easy to prove in the symmetric case. So when A equals B, then this inequality simply says that the number of triangles in a triangulation of 2A, with the meaning I just described before, is at least 4 times the number of triangles in a triangulation of A. And this is simply because if you take a triangle, then in the subset 2A, so these points will be doubled, and then the midpoints will appear in the subset, and then every triangle gives rise at least to 4 additional triangles. So this is the simple geometric proof, and the only proof that I will spell out in this talk that this inequality holds when A equals B. So having such a natural explanation for the symmetric case, we expected that it should be one could prove it in general for 2 distinct sets. So another thing is that if you take 2 homothetic copies of convex lattice polygons, the ones that I was mentioning before, then it follows directly the inequality directly from the Brunn-Minkowski inequality. So you can just think that your points are sitting in the Euclidean plane, and then use Brunn-Minkowski, and so there is a relationship between the areas of the triangles and the number of triangles in that case, so you can get the same inequality. So those are 2 encouraging features of this conjecture. And another one is that in particular, it gives this enumerator, lattice point enumerator that I mentioned before, which arises from the Gardner and Grunke inequality. So that was, again, another feature of this conjecture. So, okay, so let's see. Unfortunately, we could not prove it. So what I will report here are some cases where we could prove it. And I cannot talk much about any of the proofs because, well, they are rather of geometric nature, as one can expect. But I could not find a simple way of expressing them in slides. But one result is that the conjecture holds not only when the sets are equal, but also when the convex hull of the two sets involved are the same. Yeah, so you have two sets, A and B. They are having the same convex hull, and then here, I don't know, you put points in the boundary, inside whatever they are put, and for every configuration of points which respects this convex hull, then the conjecture holds. Well, in particular, that proof also applies to the symmetric case when A equals B. And so another thing that I did not mention before is that it has the advantage that you can prove some things which are classical results in additive combinatorics just by using this inequality of triangulations, which are for the time being bound to the two-dimensional case. And again here, the inequality is always tight unless the two sets are not only sharing the same convex hull, but they are equal. And one of them, and the set is a convex lattice polygon or some strange configuration like here, which is kind of a strange example where you have these two ingredients. So that one ingredient is that your convex hull is simple, and the other ingredient is that what is sitting inside has an arithmetic structure. It's actually an arithmetic progression, which is attached to one of the vertices of the convex hull. So that's one case where we could prove it. So I will not just talk much more about the cases that we were able to solve. One is, for instance, when the two sets are not equal but almost, so only differ from a point. So that was just an attempt to use some kind of induction to prove the theorem. Another case which is simple too is the case where one of the sets is really a triangle. And actually this extends to one of the sets being the sum of sets of catenarity 3, because you can iterate the argument. And a last case is when the two sets have no interior points. So all points are in the boundary of the convex hull. So actually this result was proved before by Katzi and Hoffman. Okay, so in the remaining time, I will discuss. So one message is that this apparently natural inequality that should hold, it turns out that it's maybe not too easy to prove. Maybe we just missed the right idea for doing this. But we explored many cases, and every case had its own drawbacks. But the other one is that this is only meaningful in two dimensions, for the simple reason that the number of triangles in a triangulation, the number of simplices in a triangulation in higher dimensions is not defined by the set of points. And so in the remaining 5 minutes, I will discuss since we could not prove this completely this conjecture, try to make a generalization to the dimensions and see if this sheds some light on it. And for this, we used this notion of a polytopic subdivision of a finite set. Instead of taking a triangulation, you just subdivide the set in d dimensions, set of finite points, in a way that every cell is a polytop. And we used something which is slightly more particular, which is this notion of mixed subdivision. which has the advantage that there is some combinatorial invariant associated to mixed subdivisions, which only depends on the sets and not on the way of making the subdivision. So what is a subdivision is, so you have a triangulation of A and a triangulation of B. This means a partition of this convex hull of A and B into simplices of dimension B. And then what you do is that you find a collection of polytopes of cells in the sum set, such that each one is obtained by one simplex from one triangulation and one simplex from the other, in a way that the dimensions match. So one is I simplex, the other one is a J simplex, and A plus J should be D here. Sorry. And so that's one thing, is the way that you obtain the cells of the mixed subdivision. But the other one is that when you use cells, one is a triangle, G for instance is a D simplex, and F is a simplex in the other triangulation, that yes, for every D simplex here, yeah, unique elements A and B, such that this thing belongs to the subdivision. So just a quick example. So imagine that you have this set here, here you have another triangle. So here, when you add this point X with this triangle T, you obtain this thing here. So now here we have 3 triangles in all. So we should see only 3 triangles in the mixed subdivision, and the rest should be adding a line in one set with a line in other set. For instance, I don't know, for instance, this line here added to this line here, I guess it will produce this square here. So that's the way that you produce the cells in the mixed subdivisions. And the key point, I'm just finishing, is that you can define an invariant in the subdivision, which is for every cell you consider a weight, and the weight is this binomial coefficient, which D is the dimension and I is the dimension of one of the summands. And the thing is that now you get some invariant. So the number of these simplices in any triangulation of M is exactly the weighted sum that I defined before. So that's now producing something in higher dimensions, which depends only on the sets A and B. Well, and the triangulations, of course, of A and B. And the conjecture would be now that the same Minkowski inequality applies to this. There is something which has to be just pointed out here, is that the conjecture says that there are triangulations of A and B, so not for all of them. And from those 2 triangulations, there exists a mixed subdivision such that this inequality holds. So I don't have time to discuss much about this, but so let me only tell you that the conjecture holds for the symmetric case as before, and that just this comment that not all triangulations work. You have to only conjecture the existence of such triangulations, and that in the dimension 2, this is a stronger conjecture than the one I mentioned before, and can be rephrased equivalently by saying the number of polytopes, which are this one here means obtained by sum of 2 lines, not point and triangle, should be larger than this thing. And then we proved again this conjecture, this stronger conjecture in some of the cases that we have discussed before. Okay, so I think that's I should stop here, and so thank you for listening.
So thank you, Oriol, for a very, very interesting talk. Are there questions for our speaker? I'm looking in the queue. So I have a baby geometry question. So if you take your finite set of points in the plane and take the convex hull, and you triangulate it only using the vertices in the convex set, why is number of triangles independent of the triangulation?
Oh, well, actually, the number of triangles is exactly the number of points in the boundary plus the interior points minus 2. So this is a formula in discrete geometry for in the plane, only in the plane. But in larger dimensions, there are these strange polytopes which have triangulations with linearly many simplices, and then others which have exponentially many. So the delta is
So I could hear your talk very clearly, but but the audio for your answer I couldn't hear.
Sorry.
But maybe maybe at some point, if you have a chance, you can just send me an email, because I'm curious about the geometry of this.
Good, I will.
Thank you. Any I'm looking for questions, and I see none. So thank you, Oriol, for a great talk.